It's time to start. So hi, everyone, and welcome to the MIT Robotics Seminars. It's a great pleasure for me to introduce our speaker today, Professor Chenming Huang. Chenming is the John C. Malone Assistant Professor at Johns Hopkins University, where he's also the director of the Intuitive Computing Laboratory. He got his PhD in computer science from the University of Wisconsin-Madison, and then he was a postdoc at Yale. So his research focuses on designing interactive AI to assist and collaborate with people. In particular, he studies human-machine teaming to provide social, physical, and behavioral support for people with a variety of abilities, including children with autism spectrum disorders. His research has received a number of awards and media coverage, including from MIT Tech Review, Tech Insider, and Science Nation. He's a recipient of the NSF Career Award. He also got recognitions for his work, including a Best Paper finalist at RSS and a Best Poster finalist from RSS as well. So without further ado, let's welcome Chenming.
Thank you. Well, thank you, Luca, for the kind introduction. It's a pleasure to be here. So today I thought I would talk to you about HRI, human-robot interaction. And it's really a space that we think about humans and robots working together. And my approach to this problem space is to bring and borrow research methods from HCI psychology to study robotics technology. So before going into HRI space, I want to set up a landscape a little bit. So on one hand, we see robots as tools. Debatable, right? But I would say, surgical robots in practice are without quote-unquote intelligence, the mind behind it is surgeon. On the other hand, you have robots that function fully autonomously, as in warehouse, right? So stuff that you buy nowadays will probably handle fully autonomously by robots like this. We also see this in manufacturing, especially car manufacturing. A big chunk of the process is fully autonomous, right? So if you look at this picture, there's no interaction. There's one person, right? That person is stand outside of the cage of the robot, right? The robot's moving so fast, very dangerous. The person is there just for supervising, right? Just to check everything's go. It's okay. So there's no collaboration. But we're moving a space where from these two extremes to somewhere in between, where we see people are working with the robots, hopefully side by side, and see robots as collaborators, as assisted partner. And we're not just seeing this in manufacturing or seeing to different sectors, hospital and hotel. I actually see this robot 2 weeks ago in LA. It's pretty fun to see that in actions. So they're really coming to a lot of human space, but not just in public space, but also in more personal space, right? So robots for education, for in-home assistance, and all that, right? So we're seeing, obviously this is not like widespread, but we are pushing a lot of research effort into the space of bringing robots closer to people to provide everyday support. Just to give you one example, I'll use children with autism as a motivation example, right? I want to start with this CNN footage to show you how robots might be an assistive and collaborative partner for humans.
Children with autism often have a hard time talking with or even looking at human therapists, like this boy. But look at how he lights up with Milo.
We found that.
So over the years, we have seen empirical evidence like this, where this population, children with autism, people with autism, they got more engaged, more interactive with machines in general, right? Computers, robots. So we thought there might be an opportunity here where we can use social robots machines to model behaviors that we would like these children to pick up. So we did this a few years back. It's Jibo. I think many of you may recognize this. It's a fully autonomous system where we have a social robot. We have a big touch screen. We have some perception system in the back just to sense what's going on, and based on sensing, and the robot will adapt its behavior. And the big screen just to deliver educational contents for practice behaviors. So with that setup, we build in two foundational social behavior. One is making eye contact, right? So as the person moves around, the robot tries to make eye contact with the person. And that's the behavior we want to model for these children. The second core behavior that we build in is share attention, right? So if you look at the screen, I'll look at the screen with you as if we are sharing attention, right? And this, again, is a core skill that we want to model for these children. And building on top of these two core social behaviors, we build a very rich interaction behavior for this setup. The idea is we are deploying this system to people's home for 30 days. And throughout the 30 days, the family will interact with this robot and to learn and pick up some social behaviors modeled by the robot. So this is a demo video. I want to show you what it looks like. Each day, the robot will provide some motivations and engage with the children for 30 minutes through gameplay. And through gameplay, the robot model behaviors. So this is what it looks like.
Yay! Hi, Eliza. It was really hard leaving my family a few days ago when I had to board my spaceship. Goodbyes can be really sad. I held on tight to prepare for landing. Then, I heard my spaceship splash into the water, and I opened my eyes. Looking around, I could see that I was safe and okay. And I could see that I had safely landed on the beautiful planet Earth. Each day I will have some games to play. If we work together and finish all the day's activities, I will earn back a piece of my gear. Thank you so much for helping me fix my space gear. I'm really excited to play. Which game would you like to play first today? Nice choice. Let me get the game ready. Very cool.
And all these game activities are designed based on our collaboration with our collaborators. And these are actually activities they do in person. You just change that to digital version. So through gameplays, the robot provide encouragement, provide feedback, model behaviors. And we just put this system out to people's home for 30 days. It's very exciting. And we learn so much by deploying robots in the real world. Some quick results. We are supporting triadic interaction because at the end of the day, we don't want the child just to learn how to interact with the robot. We want them to learn how to interact with people, right? So how to transfer that human-robot interaction to human-human interaction. So that's why we try to facilitate this triadic interaction. Day 0 is the day we go in, deploy a system. Day 30 is the day we go in to take out the system. Before day 0, day -30, we measure their skill clinically. Day 0, we measure their skill again. Day 30, we take out the system. Another 30 days, we measure their skill. So what we're seeing is there are some benefit with this robot facilitated practice. That's significant over the 30 days. However, that benefit did not sustain over time, right? So once we took out the system, after 30 days, that benefit, essentially disappear, right? So this opens up a lot of questions for us. How long should we deploy the system in order to see sustained benefit? But this just gives you an example of how can we design robots for assisted roles and collaborate with people. But if you think about, yes, go ahead. No worries.
Just to understand the gray parts of the graph, is it joint attention with the caregivers, not the robot?
Yes, with human, exactly. Yeah, feel free to interrupt. But this is an example to show you how robots might be assistive. But if you think about machine at large, it's not just robots, right? So we are seeing machines come into a different form and shape, right? So smart speaker without mobility. We can see chatbots, avatars, even just cognitive aid that's embedded in a lot of decision-making systems. So the question is, how do we think about designing this type of machines to work alongside people? It's pretty much a very difficult space. And the growing power in computing in general just make this a fairly realistic future coming years. Right, so just give you a sense of how rich the design space is. I'll use human-robot interaction as a setup, one person, one robot, right? On the robot side, we see various embodiment, right? Different shapes, and different shape just means different ways of interaction, different kind of expectation people have of the robot, right? So in my group, we look at different type of robots, social robots, mobile manipulators, even just smart speakers. A lot of my prior work in this space is how do we design and generate behaviors for robots to interact with people, right? So eye gaze, gestures, more coherent multimodal behavior. And all of this depends on the embodiment, the kind of platform that we have. Itself is a huge variables to consider. Another big variable is the intelligence behind the scene that drives the robot behavior, right? And nowadays, the modern ML tools are pretty much black box from the user point of view. How does that play into people's conceptualization of the robot's behavior? Itself is a huge box. On the human side, you have people's cognitive biases, right? Automation bias, overtrust, improper compliance, and all that. And in between is the interaction, the task, right? So the context, the state of the task, if there's any time pressures and any other type of task properties, right? So if you really think about this as a design space, there are multiple variables come into play that shapes the interaction dynamics. The challenge is that if we don't do it right, if we don't design it right, that will lead to interaction breakdowns, compromised team performance, and adoption frictions. So in the past few years, my group has been doing a lot of basic empirical research just to try to understand the dynamics of human-machine interaction in general, and use that understanding to develop new interaction methods for machines to work with people. So throughout today's talk, you will see some of these examples. There you go. Maybe, yeah, all right. The general approach that we take is a very human-centered process. We usually start from understanding how people interact with current technology, and this could happen in a lab or in a while. Could be a short-term, could be a long-term study. Based on that understanding, we build interactive systems. It could be fully autonomous. It could be Wizard of Oz controlled. We take our prototype system back to the people, not the same set of people, but a new set of people, and just to see if our new development works, right? So, and again, this could happen in the lab, in the field, over a short or long period of time. So this is a general research process that we take. So you will see some element of this throughout today's talk. All right, so I want to switch gear to talk about, given the context and research methods, I want to talk a few different projects that sort of trying to bring machines to become teammates for people. Right, so things I want to talk about onboarding, right? So a lot of human-human collaboration start with onboarding, and then beyond onboarding, how to shadow to learn the skill. During the collaboration or interaction, how do we engage in small talk for enjoyable experience? But inevitably, errors might happen. How do we think about error management and trust repair? All right, so I want to start with onboarding through task authoring. So we got this inspiration from an online study that happened during COVID. So with our robots, we built this simulation where people interact with these virtual robots by just to make a pizza, right? So the robot has access to the fridge and bring ingredients out of the fridge and pass it to the person will make a pizza out of it. So before the whole interaction, we asked participants to do two things. One is do calibration. Obviously, virtually, just drag a robot, go through different key points as if they are calibrated robot motors. The second is to demonstrate a task, pick and place, right? So drag the robot, go through a sequence of waypoint as if the person is demonstrating this is the task behavior. These two things has nothing to do with the robot performance. It's purely psychological. Right? Do these two things before you actually interact with the robot. So we thought this is an onboarding process. Without any impact on the real performance, purely psychologically, we see that just with these two tasks, people perceive their robot partners as greater than teamwork, as more commitment in the team than without the two tasks, right? So this pushed us to think about maybe it's important, and then the two tasks that they did just less than 2 minutes, right? So maybe it's important to do something before any real interactions. Maybe that purely psychological exercise would improve people's perception in general, right? So that's where we started to think about onboarding. So one of the things that we want to do onboarding is to task authoring, right? So provide some demonstration of the task. Obviously, you can think about this as down the road, learning from those demonstrations. But in our work, we didn't do learning from demonstration. We just purely do task demonstration as an onboarding process. But push us to think a lot about how to provide task demonstration. It turns out it's very difficult. Here's one example I'm going to show you. We bring the robot to older adults' home and ask them, what kind of robotic assistant that you want to have in the future, right? And this participants essentially say, hey, I want my robot to be able to clean my table, and then start to demonstrate how the robot should clean the table. And it's very difficult. You need to provide motion demonstration. You need to specify logic, switch between demonstration and specifications. And we look at this with different platforms, different setup in the lab, in the wild. It's generally very difficult for people to provide quality demonstrations. And that moves us to think deeply about how can we provide interface system to make demonstration much easier for people, right? So I'm just going to show you some example of that. So one of the things that we tried very early on is say, hey, maybe we can just programming or demonstration by situated illustration. You don't need to sit down and provide demonstration or write code. You just do illustration as if you do on your cell phone, right? So we turn everyday surface as a projection programmable interface, right? So it's a top-down projector, and you can just provide illustration on the surface, right? So you can have a circle or have something that's essentially the everyday surface as a programming environment. So you can specify, here are a set of tools I want my robot to move. Here's the area that I want the object to be moved to, and then say go. Just 3 gestures, we will be able to specify pick and place. So what we found is this approach, we call PATI, is much better than the built-in interface from the manufacturer of the robot. People can complete the task much faster and make fewer mistakes. And this kind of illustration-based approach can be very rich, right? So you can have different type of areas where you want to work with, different kind of classifications, right? So blue objects follow the blue arrow, go to that area. Yellow object follow the yellow arrow, go to that area. Wait for the person to do something. After that, the robot will be able to handle stuff in the circle area. So it's somehow expressive. Obviously, not everyday task can be solved by this level of illustration, but it's our attempt to try to bring down the barrier a little bit for everyday people to specify tasks for robots. Another thing that we try, we call demo shop, and the idea is, if you can edit your demonstration much easier, like as if it's Photoshop, right? So we are not necessarily good photographers, but once we take a picture, we can edit it afterwards. Can we do the same thing for robot demonstration? We are not good at demonstrate robot motions. There are some jerky motions, unnecessary movements, but it's much easier for us to do editing. So we take that inspiration, build this system. Essentially, after demonstration, people can go in and do a quick edit, and then output is much more quality. And hopefully down the road, it will help learning processes as well. Right, so what we show is this demo editing approach, again, is better than the building approach, which is polyscope that come from the manufacturers. People have better mental model of how the system works, and just take less time to complete the authoring tasks. However, language model came out 2 years ago, and that changed the way we think about this. So this space we call robot programming. Traditionally, it requires years of training and experience to provide quality robot programs. And we move to end-user programming, where we create new interface, new systems to make specification much easier for end users, right? So the example I show you is in the space of end-user programming, right? So we create a new interface, new system. However, at the end of the day, still end user need to provide the specification of the logic, right? So there's those certain barriers where they need to provide specifications. Now we're moving into this space where instead of specify low-level logic, we specify outcomes and have the language model to provide low-level specifications. Right? So about a year ago, we started to do these experiments to shift the programming process to become more collaborative. Right? So I specify high-level outcomes. Language model gives you low-level specifications. You can run it through simulations and whatnot. Iteratively, you refine the output and get to a point where you like it. So we're seeing this shift. We start to tap into this. We have some early exploration in this, but I think there are a lot more to explore. So the first thing we did in this is we created this integrated system that allows people to be able to provide outcome specifications with robot applications. Right? So this is a ROS package that integrates language model, simulations, and basic robot programming functionalities, and see if people can actually use the system to actually write a program out of it. So I'm going to play this demo video. We contextualize this in chemistry lab, right? So if you have this chemistry protocol that you want the robot to help you to automate, then how can a life scientist to come in and write a program to automate this process? So they don't necessarily have backgrounds in programming, engineering, but they can specify the outcome, high-level outcome specifications. So this is what it looks like. They come in and they just type what they want the robot to have to do, and then wait for some time. I mean, this is speed up a little bit, so it's not real time. And the robot will pick up and pull into, I mean, this is totally, it's not real chemical materials. You can also have, instead of provide text specification, you can make it interactive, right? You can provide verbal instructions. Say, if I finish this, you will also do the contingent actions. So we start to see some possibility of this, where language models start to help generate some robot behaviors that can work with people. But I will say, though, there's quite a bit of errors behind the scene that we have a paper to discuss it. I don't think I will have time to talk about it, but if you're interested in this, I will be happy to talk about errors in language model-generated robot behaviors. So this is the push where we use robot programming as a way to onboard a user when they start to interact with the robot. Just help them to have a better mental model of what the robot can do. The next, I want to talk about shadowing. Right? So onboarding is the initial phase. Once onboarding, you may want to have the machine to shadow your typical work processes. So our exploration here is to ask the question: what if the machine can channel the human's perspective and know how the person does the work, and how does that change the way they can collaborate? So we started with this very simple IKEA's children's chair. It's only 6 pieces, so it's actually a pretty simple assembly task. So we have people come into the lab to demonstrate how to put together this children's chair, and the participants wear this head-mounted camera, so we can capture this first-person view of how the person actually put different pieces together. Based on the demonstration, we build a task model of it, how the pieces should be put together, how they would orient the pieces for screwing, and collectively build up the structure. So once we have the model, the task model, we can then have robot to operate on the model when working with new participants, so that the robot would orient the piece in a way that's much easier for the person to put 2 pieces together and screw them into one piece. So this is general pipeline. But I want to show you today what it looks like in action. Right, so this is demonstration. Just show you the kind of data that we collected. So a bunch of first-person view of how to perform the task. As you can see, we bypass perception problem by using a lot of Apple tags. All right, so the next video I want to show you is when the robot operates on the task model I just showed you when collaborating with people.
Please screw the two parts together.
So the robot presented in a way that's much easier for the person to do the screwing. And we compare this to a robot that provide pieces based on IKEA manual. So I want to see how the person actually do the screwing. You will see some awkward movements and unproductive behavior. So have this weird hand crossing setup. What's that? Yeah. So so all the markers are just for the camera to see. Yep.
Also on the tool.
Yeah. So the tool we have put two corners. So we are not tracking the tool. We track a tool area. Yes. All right. So essentially, we compare if the robot can channel this first-person view versus just following manual. And we saw that we call it human-centric, user-centric, right? So we observe fewer unproductive hand use if the machine can channel the first-person view, and also people have feel better teamwork with the robot, and also think the robot was more considerate during the process. So this is just one example to show you how shadowing might potentially help collaboration.
Just ask this because a lot of these graphs, for me, when I look to them, they are not statistical significance, but the P is always saying it is, so I'm a little surprised.
It is statistical significance. The reason is maybe because of the spread, or maybe. So I think the effect is not great, not big, but they are statistical significant. Yeah. I would say a lot of HLI study, we don't have enough power because participants, the sample size is not as big as medical research, if you will. All right, so let's say you onboard a partner, they learn from you, and you just want to make the collaboration and interaction process more enjoyable. All right, so we started thinking about, could small talk play into this? All right, so remember earlier I talked about in manufacturing, especially small and medium-sized manufacturing, they are employing quite a bit of collaborative robots, like robotic arm. And now, if you look at those robots, they are just working with people in silence. There's it's like, I pass you this, I do this, I do that. But if you think about human-human collaboration, it's not silence, right? People talk. Hey, how was your weekend? Did you watch the football? So if we are really moving into the space of human-robot collaboration in workspace, how small talk might make the collaboration much more enjoyable. That's where we started to think about this. So how small talk might shape dynamics of human-machine collaboration, especially do people react to small talk from a non-human-like manipulator, like a robotic arm? If they do, how do they respond? So that's the research question we want to explore. So I want to play this video where the robot is working with a person to have this assembly task where the person can request different pieces, yellow pipe, green pipe, and the robot can pick up different pieces, pass it to the person, and the person, based on some instruction here, will put together a structure. And along the way, the robot will try to engage in small talk. So this is what it looks like.
Bring me a green pipe.
Fetching it now. By the way, do you like to travel?
Yes, I do like to travel. Do you like to travel?
They arrived in the U.S. from Turkey in a large box.
Bring me a yellow pipe.
Fetching it now. from that, I have not traveled much myself.
So do you like United States or Germany more?
I do not have personal preferences. I am just here to assist you.
I heard Germany has good chocolate.
Let me speed up a little bit here.
Anywhere in the U.S. you would like to visit?
I've never been to Las Vegas, and I heard that that's a fun city to visit. Bring me a green pipe.
Fetching it now. What do you hope to do there?
Probably gamble. So go to the casinos, maybe lose some money, you know. It's more for the experience, right?
So the conversation goes on, and the robot say, that sounds like a good plan. And the person say, no, that's a terrible plan to lose money. But this is our exploration. We have 20 participants coming to the lab to do this. 18 out of 20 engage in conversation with the robot. So the robot asks questions, they respond. Response varied, right? Some of them are pretty short, some of them are very long and quote unquote meaningful. 9 out of them actually ask questions back to the robot to show interest. I'm just answering question, but also I show some interest in you. Here's another example, right? So robot, on another note, do you like to play games? Participants, I like Tetris if you ever play that. Can I get another yellow pipe? No, continue the task. The robot, getting it now. No, I have not. Participants, you might like it, right? Robot, can you tell me more about it? Participants, just to start to gestures, and no, it's pretty classic game, you know, different shapes, pieces dropping down, you know, you try to clear the line and whatnot. They even make a movie about it, right? So it's sharing information that's beyond the question asked by the robot. So we thought this is interesting that people have small talk conversation with robots that do not have human attributes. Yes.
How did you get the robot to engage in small talk?
Yeah. So this is support study. This is Wizard of Arts. We are now building a system that can actually do this fully autonomously, right? So the backend will be a language model, and then the task model that we have. So we are building that. But the one I show you, this 20 participants, it's an exploratory study with Wizard of Arts set up. All right. So during collaboration, during interaction, errors happen inevitably, right? Errors are unavoidable, unexpected, and they have undesirable impact. Right, just want to show you how unexpected it could be. Here is a similar task set up. The robot will pick up different pieces as requested by the participants. Given the instruction, the participants will put together some 3D structures.
Give me a green pipe.
Give me a green pipe. It was a little bit low. And these are fully autonomous system. And during the transportation, the robot dropped by accident, right? So it was not planned. But what we observe is people react to errors like this. And we've seen this kind of social reaction to mistakes all the time in different scenarios, different robotic platforms. People all react. Even with different embodiment, like smart speakers. When smart speakers make mistakes, people react. They might smile, they might frown their eyes, all different kinds of social reactions naturally coming out of people. So that's where we start to think about, what if we can tap into this natural signal coming from people? That traditionally, if you want to do error detection, you need to have fairly good task model, and every time you deviate from the task model, you know something's wrong, right? But right now we're trying to say, hey, what if we don't have that knowledge of the task? So we essentially tried this out and use social signal as an early detection method, and much more flexible in terms of not confined by the task model, right? So we get people's facial reaction, especially the action unit, and based on that natural reactions, we do some fairly simple modeling process and estimate when the error might happen. So this is a video to show you how that might look like, right? So we have, again, similar setup, camera system to detect it. What I'll show you is, I think the volume here will be pretty low, so I'll try to repeat. What I'll show you is the system detect something might be wrong and say, am I doing okay? And the person will say, you're not, and therefore will continue to do the repair. As opposed to traditionally, the user will need to say, no, error happens, let's go and fix it, right? So instead of waiting for the user to do the explicit command, the robot will try to initiate this process.
Give me a green pipe.
Give me a green pipe. So did not pick up, and this is intentionally. Am I doing all right? Because the subtle facial movement. So then the robot went on to repair it. But just show you the possibility of using this natural social behavioral signal as a way to identify potential errors. But not, I mean, there's some false positive and stuff that I'm happy to talk about those edge cases. But if you think about detection, it's only the first step in the whole error management process, right? So once error detected, how should we go about handling it, right? So we started to think about verbal trust repair. So when something goes wrong, how do we repair the trust that got lost? And we studied this using smart speakers, right? Custom smart speakers, right? So I will play this video as a context so that I can explain how we studied this, right? So it's a common intent recognition errors, homonyms, right? So here's what it looks like.
Phoenix, add self-rising flower.
Okay, I found a dozen roses. Should I add to cart?
No.
Let's try that again.
Phoenix, add baking flour.
Okay, I found King Arthur flour. Should I add to cart?
So we intentionally manipulate the machine's error and see how we should do trust repair with this. Right, so we explore two strategies. Right, just one is one strategy, which is apology. And we manipulate the apology, right? So the attitude of the agent and then blame assignment, right? So serious attitude versus casual, taking the blame or shifting the blame, right? So serious attitude, I'm sorry for the inconvenience, versus casual, sorry for the mishap. Taking the blame, I have difficulty distinguish between homonyms versus shifting the blame. The engineering team must have made an error in the system update last night, right? So trying to shift the blame to the human team. So we essentially want to see how the machine should apologize in order to gain the trust back. So what we found is you need to really own mistakes seriously in order to, people will perceive it more likely and more intelligent, and have higher satisfaction of that service. But if you think about trust repair strategy, it's actually more nuanced than this, right? So along this line, we look at a similar setup, but we start to see a few different factors play into trust repair strategy. The first one we saw is actually there's some gender bias that come into play. So here we have three different variables that we manipulate. We look at. One is participant's gender, self-identified gender. The second one is the voice sounding, right? Could be sound like female agent, male agent, or neutral. And the third is repair strategy, either apologize or provide compensation. So the results I want to highlight here is Male participants interrupt the arrow much more compared to female participants. It's independent of the other factors. So here I'm going to play a video. It's a bit extreme example, but this happens. But to illustrate how male participants might interrupt the interaction.
Okay, I found green tea clay face mask.
Yeah,
Should I add to cart?
Yeah, add that to cart.
Got it. Item has been added to your cart. I will give you a $10 credit that can be applied to your future purchases with us for the inconvenience caused.
Oh my God.
So obviously this is one extreme example, but that just shows how tricky it is to really think about designing this repair strategy. So gender might come into play. Power dynamic might also come into play, right? So in another setup, we also look at repair strategy, but in the context of human-robot collaboration. This time, the robot is helping the participants to make this pasta, I believe. The robot will pick up different ingredients and pass it to the robot, and we want to see how power dynamics might influence the effectiveness of trust repair strategy. Just show you this manipulation check that we did. The way we manipulate power dynamics is through robot speech. The robot either say, hey, I know how to do this, I'll pick up ingredients, I'll pass it to you, versus the participants will need to request ingredients one by one from the robot as the robot is learning this recipe. So what we found is if the robot had higher authority, then it's much easier for them to gain the trust back. Obviously, it's a perceived trust. There are some differences for different strategies, but the effect there is much smaller compared to the power dynamics. So if the robot has a higher authority, projected authority, then it's much easier for them to influence participants. What's interesting to us, in addition to that, is we actually see quite a bit of improper compliance from the supervisor robot, right? So we don't see that from a less authoritative robot, but see that from supervisor robots. So what is the improper compliance? Here's one example. Robot now chop and add sausage to the pot, but then pick up a mushroom instead of sausage. And participants actually recognize that it's a mistake and say, what if it is wrong? You pick a mushroom instead of sausage. But then the participants continue to chop the mushroom and put it into a pot. It complied, even though they recognize it's a mistake. So this is concerning, right? Especially given this is a toy lab study. We have a similar study, but not in the space of HRI, in the space of AI8 for human radiologists. We have a 20 human practicing radiologists. We manipulate the AI suggestions, performance. Well, we're seeing a similar patterns where even expert humans are following erroneous AI suggestions. So, we are starting to think more about how do we think about improper compliance and how do we design strategies to calibrate that. So this is some of our initial effort into thinking about trust repair and how different factors might play into trust repair. So I have quickly went through a few different projects that how we can put together for thinking about designing teammates for machines. I think that this problem space is very, very big. There's a lot of research questions that we haven't really explored and excited to explore. I want to talk about a few additional things that we're excited about. It's ongoing work where we think about this ad hoc collaboration, right? So a lot of examples I showed you earlier is one person, one machine, right? And their interaction is fairly prescribed in the sense that you do a set of things, I do a set of things, there might be some collaborations. It's pretty prescribed in the sense of, we know what we're supposed to do. But if you look at human collaboration, it's pretty ad hoc, and the collaboration emerged. And it's more than just a two-party collaboration. So we recently got this support from NSF to look at this ad hoc collaboration. So I want to play this video to show you what it looks like for a human to collaborate ad hocly, right? So we want participants to build this large-scale bunk bed using PVC pipes. We project what the bunk bed should look like on the wall. We didn't provide them step-by-step instructions, but just say, hey, that's what it should look like. Go and figure it out. So this is what it looks like with a team of 4 to put this together. So it's incredibly fluid. They make plan. They make plan as they go. A lot of multimodal communication, a lot of collaborations. The teams got moved from sub-team to sub-teams. They did a lot of small talk, actually. So we are now in the process of collecting data on how people engage in this level of ad hoc collaboration. What are the underlying principles and processes that give people this ability? And hopefully, based on that understanding, we will provide something for robotic assistant that can engage in this level of ad hoc collaboration. So hopefully, in a few years, I have more to say about this. But we're pretty excited about this ad hoc collaborations that we see in humans. Another big line of work that we're pretty excited about is put the robots out there in the field over a long period of time. Very similar to the Jibo example I showed you earlier, but we are now looking at older adults in local community at Baltimore. We're only able to pick this up about 2 years ago, because of COVID, but we're finally able to bring systems out. So our approach is just bring the system, put it there, get feedback, right? So we do different kind of systems, mobile manipulator, even smart speaker. This is an example that we actually just finished a deployment for months where we integrate ChatGPT with Alexa Skill such that the voice assistant actually can engage much more conversational interaction as opposed to just one single term conversation. So we got very rich data sets. So it's interesting to see how people actually have this very fluid conversation with voice assistants over 30 days. So I'll probably be able more to say on that in a few years. I think I'm short on time, but I want to quickly show you some of the deployment system that we're doing. We use this robot to promote physical activity as an example. Motivation. We just don't engage in physical activity enough. Not just older adults, but young adults like myself too. The question is, how can we use social robots as a way to promote physical activity, right? So we went through a very in-depth design process with local participants, through interviews, co-design workshops, get the functionality requirements, robot design ideas. And our participants tell us that, here are 2 ideas that they like. One is we remake this based on their hand drawings. One is really like social robots that can provide encouragement, social support. The other one is really just physical. Their idea is really futuristic, right? So when you're about to fall down, there's a spring, just jump out. I think it's going to be very difficult to do, but the idea is to have some sort of physical assistant like exoskeleton. So we pick up these 2 ideas and we just, run with it. So we build a robot system, social robot system that very similar to the Jibo setup, have social robots, a screen that show educational content. In this case, exercise program. We track their pose during the exercise, and based on that, we provide feedback. We put this system out with these participants over a week. We got a lot of feedback. Now we're incorporating those feedback to the design and refinement. Hopefully, we'll bring the system out again to the different participants for a longer period of time. For the physical system, we actually started collaboration with folks at NC State. We got this new support from NIH to study this very lightweight exoskeleton, and for people, older adults, to do just walking exercise, right? So we are doing feasibility study and about to try it out in the community. So very excited about this. Again, in a few years, I might have more to say about how this kind of assistive device or robots, if you will, my benefit older adults. So with that, I'll stop here. Thank you for your attention, and I'll be happy to take questions.
Right, folks. Thanks. So we have time for a few questions.
Hi. Very nice work. I've been following some of it for the past few years, and especially Maya's work on failure detection, which is similar to some of the work I did on my PhD as well. And I was wondering now I think there's a lot of HRI work emerging on failure detection models, but it seems like we actually stopped there. So there's not that much on management, and you mentioned some of that work as well. How would you see? So once we have these models and they're actually useful, how would you see that we can actually utilize these models and also utilize explainability methods to actually to not only recover from the failure but also use these methods to portray what is going wrong, to use it basically as an interactive element. Would you see any connection with this?
So you're saying that can we use that as a way not just improve the people's perception and trust, but also use that as an input back to the machine system to hopefully improve their machine performance? So very good questions. We didn't do anything about that space yet, but I think so. What we're thinking is if we want to know where things go wrong, we need more than just facial expression or just those cues, right? So one thing that we're trying to explore is through eye gaze, like where people look at might tell us about where their expectation or their debugging, right? So where they think might go wrong. So that might give us some cues, but we don't have much work in that space. If you have some ideas, we'd love to collaborate. I know you guys have some a lot of prior work in that space that inspired a lot of our thinking in this as well.
Yeah, not any particular ideas, but I'm also curious how we could actually approach the problem in that direction.
Yeah, if I would guess, I will try with eye gaze, just most because we have more experience in that space.
Thanks.
Yeah. So right now the estimation model in that I didn't talk in detail, but that allows us to estimate when the error might happen, but not where. Right, so if eye gaze can tell us a bit about where, then that might be a place to think about what actually goes wrong. Good question.
Let's see if there is more. Maybe a last one. So there is a lot a lot of the slides are thinking about this assembly task, with a specific robot and so on. I was wondering, many of the conclusions somehow are task-dependent in the sense that, of course, onboarding is important, but for example, the small talks. I imagine that, for a robot which is fairly slow and for a task which is very slow, that makes a lot of sense. But if you start having, a very quick task, very efficient motion for the robot, it seems more of a way to kill time while you're waiting for the robot to execute. Maybe there is no need for small talk if the robot is very fast. So,
No, that's a good question. Yeah, so the small talk project is really exploratory, and that actually opens up a lot of questions that we're thinking now. For example, when to do small talk, what topics to talk about, and is it okay to just keep doing, right? Because if you think about human-human conversations, like you said, when we are trying to kill time, we'll do small talk, but if we're already into the task right now, we're not, right? So how do we understand when to engage in small talk is something that we just start to think about after that exploration. But I think, but to what our surprise is, people really actually buy into this idea to be able to talk to a manipulator. And we did this last summer, right? So one potential explanation is because of ChatGPT or any other language model that just make people start to think that conversation is a sort of a theme with the machine now, and therefore they bought into this idea. But honestly, we don't really know why we are seeing that kind of behavior.
I can see also a downside in which maybe language right now is more advanced. Maybe the manipulation capabilities, maybe the small talk is kind of making the user overestimate the capabilities of the robot?
Yeah. Yeah, we also got that feedback as well, right? Because once you engage in this small talk, people have this social intelligence expectation from the robot, and the reality is the robot cannot do much. So that might actually break the mental model.
I have actually a related question, and then we see if there are others from the audience. The demo that you had with the language model for the onboarding part, can you tell a bit more about that? So I think this is the one in the chemical type of lab in which you're dropping samples and so on. So in language, I guess you're specifying some goal, and then what happens? What are the intermediate steps to get to the robot? How do you connect to the embodiment and the skills of the robot?
Yeah, I see. Okay, let's see if I understand fully. So there, we provide a few system prompt. Right? What's the robot's role? What are the basic context? Right. So from the user point of view, they just need to specify a specific action. Right. So pick up tube number 5 and pull it into this beaker, for example. Or they can do more collaborative, like as voice input. Say, hey, when I finish pulling this into the beaker, you pick up tube number 2, for example, right? So the conditions that specify the user are translated into the robot's, translate into the code generated by the robot. So we don't necessarily, so the task context is provided as a system prompt in the very beginning, not during the coding process.
So in the prompt, you specify even the location of things in the environment?
Not necessarily location, but there are some AR markers, right? So yeah.
Got it.
But not the full perception system, just based on the marker detection. Mm-hmm.
I'm really curious about the interruption part of this. And you were talking about there's male and female. You gendered the speaking subject, the people. Mm-hmm. Did you do a similar thing about the gender of the voice?
Yeah. So
was that in there? I couldn't quite tell.
Yeah. Yeah. So the result I show you that male participants interrupt more. It's independent of the voice gender. Yeah, so it doesn't matter that the voice gender is female sounding or male sounding or neutral. That we are seeing similar. Yeah. It's just that we interrupt more. But going back to the earlier comment, again, it's a lab study. It's reasonably small sample size. So how much to generalize this also require more work. Yeah.
All right, so we're past the hour. So thank you so much, Xianming.
Thanks.